Okay, 10-4. Central tendency and variation. We did central tendency last time. There were 3 types of central tendency. They were what? Mean, median, and mode. It's all the M's. It's like, okay? All right. So today we're going to talk about variation. So central tendency is how things are grouped up. Variation is how they are spread apart. And any data set has both features, okay? So the first type of measure of variation we're going to talk about is called the range. So the range is simply the difference between the biggest value and the smallest value, right? The tallest person and the shortest person, the highest grade and the lowest grade. Okay, whatever those numbers are, that's what we're looking for. The biggest value minus the smallest value, it's range. There are 3 others here on this same slide because they all kind of go together, and then there's one that got left out because it's just not enough space on the next one. But they're the lower quartile, the middle quartile, and the upper quartile. So quartile should sound a lot like quarter, right? And that's exactly what it is. It's the 25% mark. So the median is the middle value. It cuts the data in half. So we talked about that last time, right? We have the tallest person down the shortest person. The person in the middle is the median. And so then if you take that middle value and you go down to the bottom, right, the lowest value and the middle value, and you split it in half again, then you have the lower quartile, the 25% mark. It's the value, 25%, right, whatever it is, that 25% or 1/4 of the people are below that value in whatever you're looking at. Height, weight, IQ, head circumference, it doesn't matter what we're looking at, it's the bottom 25%. And then you do the same thing on the top half. It's the top 25%. Okay, so a place where you sometimes see this used is in percentiles, which we'll talk a little bit more about specifically, but quartiles is a type of percentiles. And so people do this with heights and weights of children, head circumferences of children as well. You see these used on testing, right? The top 10% of the people did XYZ. So sometimes schools, like colleges, will use their scholarship criteria in this way. So if you were in the top 10% of your graduating class, there's a certain category for scholarships, right? That's percents, but the quarter is what we're looking at here. So a quartile is a 25% mark. And then the next one is the interquartile range. So the interquartile range, it goes from the first quarter to the third quarter. I feel like I'm talking about a football game or something, okay? First quarter to the third quarter, and it's the space in between there. So it's not the biggest and the smallest, that's range. It's the 25% mark and the 75% mark, and that's the interquartile range. You also have the lower extreme, which is your smallest value, and the upper extreme, which is your biggest value. And what we're going to do here is we're going to create what's called a box plot. Some resources will call this a box and whisker plot. Okay, like a cat, box and whiskers. And it uses all these things that I just described as pieces in the picture, right? The graph that we're going to do. So it uses the lower quartile, the upper quartile, the median, the interquartile range can be seen on there, and then the lower and upper extremes. And we're going to use the same data set that we used last time that's super arbitrary with no data, like units on it. We're going to use that same one. So here's our data set, and what we did last time is when we did this is we found the median, the mean, and the mode. And in doing the median, which is part of this box plot, we had to actually list them from smallest to largest. Everybody remember doing that? Okay, we're going to list it from smallest to largest again. So it starts at 12, and then it went to 17. We had 2 18s, 2 22s, and a 30. And we isolated, because there's even an odd number, of these, so we could evenly divide this, and we could find the exact middle. It was this 18. So this 18 mark here is our median. We're calling that our middle quartile now. It's called Q2. And if I have the median value, like I do here, as part of my data set, what I do next is I look at these lower ones and these upper ones as though they were their own data set. Okay, so if I look at the lower part, everything below the boxed Q2 value, those 3 values, what's the middle value down there? 17. It's 17. So this piece right here would be Q1. And if I do the same thing on the upper part, what's my middle value? 22, the second 22, right? And so this one's Q3. Now, if I've listed them in order, like I just did, it's also very clear and it's easy to see that this is my lower extreme. And this one over here is my upper extreme. I'm just abbreviating. There's nothing special about me labeling them that way, but that's just a reference point for myself. And so we are going to draw a box plot. Wow, that's not what I wanted at all. Let's try again. So in a box plot, you're going to have kind of a number line that's going to set underneath your box plot. It's not part of the box plot. It just gives us a reference point, like to know where we are kind of thing. But it needs to include all the values that you just looked at. So it's going to start with my lower extreme, which is 12. And it needs to go all the way to my upper extreme, which is 30. And this is a small enough data set that I'm going to label every point. So I have 12, 13, 14, 15, 16. These should be evenly spaced or as close as you can kind of get that. 17, 18, 19, 20. I've made mine too big. I'm going to have to shrink it, but we'll get there in a second. 21, 22. It's got to go all the way up to 30. Twenty-three, 24, 25, 26, 27, 28, 29, and 30. Okay, so they look fairly evenly spaced. I think they're okay. I'm going to make a dot above the line at each of those values I just identified. The lower extreme, Q1, Q2, Q3, and the upper extreme. Okay, I'm going to make a dot on all of them. So I have the lower extremes at 12. I have my Q1 at 17. I'm going to try to make them about the same height. And then I have a Q2 at 18. I have Q3 at 22. And my upper extreme is at 30. Okay. I need those locations marked, and these dots are not super special. You could skip this step, but they give me a place to mark things so that I can see them easily without having to keep looking down below. These are my 5 points of interest. The median, 18, you're going to draw a vertical piece through that dot. And you're going to do the same thing at the 17, which is the Q2 value, and at the 22, which is the Q3 value. And what you're going to do is you're going to make a box right here, like this. Good grief. Why isn't it starting there? There we go. So this box represents the middle 50% of our data values. It's the interquartile range. I've got from Q3 down to Q1, and I've got Q2 in the middle. And then what I do on the outsides is I connect those dots like this. This is why it's sometimes called a box and whisker plot, is it looks kind of like those long pieces or whiskers out to the side. So it gets called that sometimes. This generalizes the data. I lose the specificity. I only know of 5 specific values, possibly only 4 specific values, depending on how the median works out, that are actually in my data set. But it shows me some nice groupings. For example, it shows me that this value over here at 30 is kind of an extreme value. It's really far away and there's not much in between. And I know there's not much in between because this is 25% of my data in that right side whisker. And there's 25% my data on the left-hand side. So the data is more concentrated, is the word I want, more concentrated on the lower part than it is on the upper part because it's less spread out. You can also see that compacted piece in the middle. you can see what the Q1, Q3, and Q2 values all are. They're all present on there. And as with any graph, we need to have a title. And I don't have any data on here to actually write my title, like to give it a description. So I'm just going to write title here to remind you that when we have units, we would need a title. Okay? So this is one way to show how spread apart things are, the variation of the data. Let's do our second one. The second one is called the mean absolute deviation. I will abbreviate that MAD. This makes use of the absolute value to find the difference that each data point is away from the mean. Notice it's using the mean, not the median. And it's found by taking all of the absolute value differences and then averaging them. I'm going to do an example of this, but I want to do it within the construction of a different example. So I'm going to show you one other type of variation before we do this example, okay? The next one is actually called variance, and then standard deviation at the bottom. These two things go together. Variance finds the mean, which is what we would do for mean absolute deviation as well. It subtracts the mean from each number, which is what we would do with mean absolute deviation as well. But step 3 is where it changes. It actually squares the difference of the steps, or difference from those values. I don't know what it says from step 3. It should say from step 2, because there is no step 3. It is step 3. I don't know. That should say 2, and this should say 3. There we go. That makes more sense. And then you find the sum of the squares that you found from step 3. And the last thing is to divide by the number of values. So it's sort of averaging something as well. However, while variance is found in this way, standard deviation is just tacking on a step number 6. And that's usually what we're asked to find is standard deviation, not variance. And what standard deviation does is kind of undo step 3. Step 3, you squared everything, and in step 6, you square root it. Okay? So this is the square root of the variance, and basically it's just the 6th step of this process. So we're going to do an example, and the example is going to be done within a table. The first thing we're going to find is the mean absolute deviation. The second thing we're going to find is the variance, and then lastly, we're going to find the standard deviation of that piece. The data that we're going to use is the same data set that we've been using throughout, right? We've done several examples with this. We just did one. And if you go back in your notes, you'll actually find out what the mean is. Mean is often written with an X with a bar on the top for average. And I believe we found that it was 19.9 last time, was the average of these values. So here's the way that this works. We're going to make a table. I'm going to include all the data points, even if it repeats. I'm going to include it twice or 3 times or whatever, okay, in my set. Now, you can put them in order from smallest to largest if you wish, or you can just go with the order they give you. It doesn't make any difference. I'm going to go with the order they gave me. So I have 18, 22, 22, 17, 30, 18, and 12. So far, so good? Just listed them all there. Okay. This step here, I'm going to actually do this as an absolute value. So I want the absolute value of these x values minus my mean. And this mean right here is the 19.9 that I got. So I'm going to write them all out in this step and find their value so that you can see what that looks like. So this is supposed to be 18 minus 19.9 and then the absolute value. This should be 22 minus the 19.9. I have another 22 minus 19.9. I have 17 minus 19.9, 30 minus 19.9, 18 minus 19.9, and 12 minus 19.9. Do you have to write those out every time? No, you don't. I'd like for you to know where they came from in your notes, so when you look back, you're not like, how did we get that number again? What did we do? We're going to take the subtraction. Now, because this is absolute value, if you just take the bigger number minus the smaller number in each of these cases, you'll get the positive value, right? So like up here, I don't really need to do 18 minus 19.9. I can do 19.9 minus 18, that's fine. And I will get the same thing because I'm taking absolute values. So what's the difference between 19.9 and 18? Well, it's 1.9. How about the difference between 22 and 19.9? Anybody have a calculator? Just grab the calculator. This will make it go a whole lot faster. It is 2.1. Here's a couple of those. How about 17 minus 19.9? It's 2.9. 30 minus 19.9. Mm-hmm, 10.1. 18 minus 19.9, I already did that one. That one was the first one I did. It was 1.9. How about 12 minus 19.9? 7.9. And then what I do is I add them all together. Okay, so grab your calculator, add those values together. $28.9. And then we're going to find the average. And the average is to take the sum and divide by the number of values. So how many values are there? 7. And if I divide that, what will I get? Okay, we'll use one decimal, so 4.1. Okay, are we good? Yeah? Okay, this table, everything that we did, is going to show up again in the other problem. Okay? And it'll have a few more steps. So all these pieces that we did before, we're going to do again. We're going to find variance. So the variance is going to be to take each of our values and to subtract off the mean. So I have my x. Okay, here we go. And I want to do x minus the mean. So I have 18, 22, 22, 17, 30, 18, and 12. I'm going to take the same values that I had from before. So I had 1.9, 2.1, 2.1, 2.9, 10.1, 1.9, and 7.9. Okay, everybody good? All right. This is where, so we've done, let me look at this list with you. We've done step 1 and step 2. We found the mean, which we had already, and then we subtracted the mean from each number. Step 3 says to square them. So we're going to take calculator, you're actually going to really want one now, and you're going to square 1.9 and 2.1 all the way down. You're going to square each of those values. So you're going to take x minus x bar, what we just did, and you're going to square it. So what is 1.9 squared? Thank you. Taryn, you want to give me all these values? Do you? No, you don't. Somebody volunteer to give me some values. Goodness, y'all are quiet today. Okay, 4.41. Thank you, Cabriana. And there's a couple of those, right? Okay, how about the 2.9 squared?
8.41.
Thank you, Callie. 8.41. How about 10.1 squared?
2.0.
Thank you, Chesney. 102.01. How about 1.9? Oh, we already did that. That's 3.61. How about 7.9? It's our last one. Squared. Yes, Avery. 60, what was it? 62.41. Okay, so that's step 3. What steps 4 say that I'm supposed to do? Find the sum, just like it on the last one, except that it's a sum of different values, right? So what do we get? What do we have when we add those together? That was step 4. Step 5 says I'm going to find the average of that. So I'm going to take those, or take that value, and I'm going to divide by 7. What does that give me? All right, so and if I do one decimal, it'll be 27, right? Or 27.0. Now, 27.0 doesn't have a whole lot of context for us. This is really just leading us up to finding the standard deviation, which is part C of this problem. And in the standard deviation, what we do is we take the square root of the variance. So what is the square root of 27, excuse me? So 5.2 if we do do one decimal, yeah. So it's about 5.2. So this is talking about how things are spread apart, how things are varied. Now, I mentioned that without a whole lot of detail because we need the next part of the lesson to talk about what this actually found, okay? So this is something called the standard deviation, and it's 5.2 for this problem, okay? All right. So all of this is leading up to, at least the standard deviation step is leading up to something called the normal distribution. The normal distribution is what you've probably heard of before as the bell curve, okay? So this is a smooth bell-shaped curve. Looks like this. That's not great, but you got the idea, I hope. And it depicts the values distributed symmetrically around the mean. So right here in the middle, that's the mean, and things are symmetrically distributed around them. Now, when you have large enough groups of things, they distribute with the bell curve, right? This is one of those statistical analysis kind of things that people do. So like if you go to the grocery store and you bought 500 boxes of Honey Nut Cheerios, what you would find is that the weight that's on the box is not precise. It's not always exactly 12 ounces or 20 ounces or whatever it says on there. But if you took all of those boxes and you really weighed them and you added them all together, the mean would be, let's say, 20 ounces. And then everything else would spread apart from the mean in this nice bell-shaped curve. The majority of the values are still going to be really close to the 20 ounces. But there's going to be some extremes. Have you ever gotten one of those bags of chips that's so full and you're like, man, score, that was awesome. It's definitely not 1 ounce. That was so for sure 2 ounces of chips. Or have you ever gotten one of those bags of chips that there's almost nothing in it? Because I have. I've had both things happen before. This is the bell curve, okay? There's an averaging of things that are going on, and it's in this bell-shaped curve. Here's the deal. 68% of the data is within one standard deviation. That's the thing we just talked about, right? Standard deviation. 68%. So 68% is bunched of the area, if you want to think about it that way, is bunched up right here in the middle. 68%. And if you go out 2 standard deviations, something like this, so from here all the way over to here, the area underneath there, it's 95%. And if you go out 3 standard deviations, you practically get everything, and it's 99.8%. So if you go out here far enough in both directions, you're going to get from here all the way to here, shaded underneath the curve. It's going to be almost 100%. It's 99.8% of the data. Okay, so let me give you a real quick verbal example of this because we've talked about this recently. Do you remember when I talked to you about Huntington's disease? All right, you remember that, right? And I told you my brother doesn't have it, right? My dad did. So Huntington's disease, average age of onset is approximately the age of your parent that had it. So if you know that the average age of onset is, say, 45 years old, which is somewhere around when my dad was starting to show symptoms, so 45 years old. Well, then within 1 standard deviation of that is when 68% of the people who have it are going to start showing symptoms. So you take whatever the standard deviation is and you go backwards that many years and you go forward that many years and you could be like, hey, I'm probably 68% likely going to show symptoms between this age and this age. Are you tracking with me? Okay. And if you go 2 standard deviations in each direction, 95% chance. And if you go 3 standard deviations, you're 99.8% chance. Here's the problem with Huntington's disease. The standard deviation is 18 years. So if you're 45, like my dad was 45 when he started showing symptoms, and you take 18 years off of 45, what age are you? 27. Yeah, you're close. 27, age 27. And if you take 18 years and add it on to it, where are you? 18 plus 45. 63. So if my brother or sister and I had this disease and my dad's age of onset was 45, then that means we're 68% likely to start showing symptoms between ages 27 and 61. What a useless piece of information. You see what I'm saying? That's a huge range. The data is simply very spread out. And that's only 68%. I'm 95% likely that I can go another 18 years in each direction. And at that point, that's pretty much their lifespan. I mean, 18 years before 27, how old are you? A child. You're little, right? You're what? Did someone say?
I said 9.
9. Are we close to it at 9? Yeah, you're 9. I have a 10-year-old, like 9. You're little bitty. You're third grader. Okay? Up to what's 18 years beyond 61. I think we're at 79. Is that right? 79? 79. 79 is getting pretty much up there. And that's pretty much, you're fairly old by the time you're 79, right? You know? This doesn't give you any information. It's completely useless. So the standard deviation doesn't tell you a lot in that case because this data is just so spread out. But it does tell you a lot when the data is much more compacted, when it's tighter together. And that's what you see with things like the production of the cereal boxes, is that the data is going to be much more bunched up. So if it says 20 ounces, you're probably going to have something with a standard deviation of maybe like 1 ounce. So 95% of the boxes are going to be between 18 and 22 ounces, right? Things are going to be much more concise, more compacted to make that work. So we're going to do some examples of normal distribution. We're not going to get finished, but at least we have the time to start this one. This says to assume a normal distribution, the average phone call is 8 minutes with a standard deviation of 2. So the way that these are all going to work is you're going to draw a bell curve every single time. And your bell curve is going to have the mean that it gives you, which it says the average phone call is 8 minutes. That's my mean, listed in the middle. And then it's going to use the standard deviation, and they give us a standard deviation of 2, which means we're going to block out 2's above 8 and 2's below 8. So we're going to do 8. I'm going to go to 10, 12, and 14. And I'm going to go choose down. So I'm going to go from 6 to 4 to 2. Does everyone understand where all those numbers came from? Okay. Now, question A asks us the percent of the phone calls that last between 6 minutes and 8 minutes. So it's this part of the curve. So you do this, you're going to shade it in. Now, 6 to 8, that's one standard deviation, correct? What did the empirical rule tell us about one standard deviation? What percentage of the data? 68%. But this graph only did one standard deviation to the left. If I want to do 68%, I do one standard deviation to the left and to the right. So if it's 68%, if I go from one standard deviation to the left to one standard deviation to the right, what is it if I only go one standard deviation to the left? I'm only going to the left. No. So here's the value that I'm suggesting that it would have been. This would be one standard deviation to the left and to the right, and this blue part would be 68%. Whoa, whoa, whoa. What's that? So I'm asking what the purple part I shaded would have been. 34. How'd you get that, Haley?
Half it.
It's half it, right? I only go half of the distance. I just go to the half to the left instead of the half to the right as well. So I need to half the 68%, and I would have 34%. Okay, can you give me just like 1 second to do the next one so you can see the difference, and then we'll post the video for the rest. Okay. So same setup, we want the phone calls to last less than 4 minutes. So less than 4 minutes is this outside piece, right? How far away is 4 minutes? From the mean. How many standard deviations? 2 standard deviations. So if I went 2 standard deviations to the left and to the right, I'd have this piece in here. How much is in here, according to the empirical rule? What was it? 95%. So if there's 95% in the middle, how much is on the outsides? Yeah, 5% total, right, on the outside edges. And I've only shaded one of them. So I would take my 5%, divide by 2, and I'd have 2.5%. So it would be 2.5% of the data. 2.5% of the phone calls would be lasting less than 4 minutes.